Great to be back in Chicago. It's been too many years, and great community, and it's really a pleasure to have the chance to interact and talk with you. Since now Feathers is abandoned and he's busy, doing AI, I'm sort of the last man standing of the fossils who will talk about legacy systems. But part of the reason I still do it is because I still get, every few years I get asked, but because for me, legacy systems, and those of you who know a bit about my background, I work with a lot of exotic technologies. I used to call them weird, but a customer said, Dave, you should call them exotic. So these are everything from vector functional programming to table-driven programming and a lot of different things. And the reason I've been able to do that is because often I've been able to use them in a really, you could say, challenging or ugly legacy environment. And I've come to call this innovation and legacy. And so this is just a talk about one approach to a problem that's important now. I think we all know the story of migration. That's something, what about the migration data? What about the data migration? That's no problem. It's just going to be a few scripts at the end. And that's how the story begins. So, okay. Maybe this will work. So I don't think I need to go through this. Basically, these are stats from Bloor and Gardner and whoever else you pay to give you an opinion that you would like. They were done, I think, particularly for Oracle. But basically, most migrations don't end up on time or a budget. I'm sure that doesn't surprise you. And so what I want to talk about is one customer. I've changed the names to protect the guilty. It's a company which we'll just call ERPRS, and they do enterprise resource planning. And they're the dominant leader for people who do have things like planes, military vehicles, big construction equipment, and all the parts and inventory to support these things globally. EPRS has been around for a while. They're hundreds of customers. They're very successful in their area. And they made a very shrewd decision at the time to use what was called a network database. A network database has the property that you can see this. Everyone in this room, I assume, knows what ER diagrams are, but I perhaps should not do that. But basically, the network databases were really designed to deal with this recursive relationship where basically something can be made of something or something can have some things in it. So basically, and this is done by representing something called a many-to-many relationship, something that most programmers don't think exists because collections only work one way. So one of the big design problems we found with people with data is that programmers don't, they don't like SQL and they don't want to know about data models in general, but they're still important in some places. So these ER diagrams actually are realized fairly straightforwardly in these network databases. And because of this implementation, essentially of rings, so it's a pointer walking navigational database, much as for those of you that are in fashion with Neo4j are doing that. So this talk, although it's historical in context, I predict that some of you in the not too distant future will be trying to figure out how to get out of a very inefficient and navigationally complicated graph database and put that into a very efficient vector store so you can actually get your knowledge out of it after you put it in your knowledge graph. So, and that's even a harder problem because property graphs are instance-based, not type-based. So basically their problem, customers have two concerns. The first one is navigating around a network database is not easy programming. You have to know how to do this. There's no query language. The second one is that all these databases are running on hardware that's obsolete with the vendor. That's the problem. So it's your typical legacy problem. So the first problem was to try and solve the reporting problem. Basically, the way it worked is that in order to satisfy the customers, ERPRS takes requests, and they have programmers who know this data manipulation language, and then they write the reports for the customers with the code and send it back and publish it, and other customers get it. They, of course, did the obvious thing, which is, I have one trick that I'll mention. If you want Agile to go away, just don't use the word anymore. It's kind of like OS2, Lotus 1, 2, 3. Just don't mention it. Anyway, they went and did this thing, and of course, they got marginal improvements. And then they tried to develop their own SQL query engine, very ambitious effort, really good engineers, but they're MRP engineers. They're not data engineers. They're not data scientists, not database scientists. So the solution, and I think this is one that's pretty well known, I call it SQLify it. Basically, is you have some ugly data source. The easiest thing to do is basically replicate out of, for those of you that made the mistake of using NoSQL, some of you may even still be doing it, you can actually make it consumable to people so they don't have to write parsers to the JSON by actually replicating the data, interestingly out to a good relational data source. So that's the first thing, very easy to do. The second thing is that there are still some applications that have to go at this complicated network database. And the solution there is to there's 3 or 4 companies in the world that make OEM SQL engines. So they're SQL in the client, and inside you basically build the code to navigate. So they contracted with one of those companies, and so they're able to do this. So the good news is they have a near-term victory. And going back to Venkat's talk, it's very important to always have a short-term something that gives people a aha, especially when you're going to do something quite risky, which we're about to do. This was not risky. So the customers were very happy. They all went to the customer meeting. Everybody saw the demo. They were going to be able to do their own reports with whatever Crystal reports, whatever your favorite query tool was at the time, and able to move ahead. So the customers get new confidence. However, the real ticking time bomb is this legacy network database. By this point, they were the only major customer on the LNDB. And the vendor was limping and quietly even called up and said, "How would you like to buy us?" The customers heard this and they panicked. This situation, by the way, is not uncommon. You may think it's. So they have hundreds of large customers. Essentially, all of them have multiple on-prem databases in geographic locations. So they're not running SaaS, right? Someplace far away in the cloud. And the customers are saying, how are we going to take our data from our LNDB and get it into a modern source? Modern in this sense is a relational platform that runs probably on Microsoft or Oracle or perhaps IBM. So that's the small challenge they're worried about. Now, of course, the conventional approach and the one that the ERP engineering team, and there's no fault, these are very talented people, but they're not database engineers. I just want to make that clear. So they're application engineers who know how to really use this database. So their idea was to write all the queries that needed to be and then once you've got all the data out, put it in a really nice format like JSON, and then take it and write SQL queries and stuff it in. This is a really hard problem. It's very hard, it's even harder to test, and the performance really sucks. This is guaranteed to be very slow. The other problem is the customers are allowed to have extensions, and this all has to run at the customer's on-prem database. In some cases, like military customers, you can't even get people into the room because you need security clearances to do this. So they make it a little harder to do. So, need an innovative solution. The first solution is if you're going to move, terabytes, well, petabytes of data, you're not going to do that using random access technology. And you're not going to do it without batch and binary. So you need a simple solution. So the simple solution, I'll be going through it, is essentially use physical access, read the naked pages off the disk, bypassing the schema. Use sort merge because we know that works and is fast. And it'll work no matter scale because some people's machines don't have very much memory in them, and old sort merge algorithms could be done on machines with 16 kbytes of memory. Not advocating that. And the inspiration we take is from something I'll call the humble linker. If you know about a linking loader, basically, you have refs and defs in your program, and what the linker does is take multiple binaries and connect those together and put them and produces an executable. So it just resolves these name matches and so on. So just a brief segue. No matter what you're using, SQL, pick your favorite query language, walking the database through the logical schema is painfully slow and error prone. So the easy way to do this is to get physical, actually understand what the database pages look like, and it turns out that a network database and the latest Oracle database, the pages are essentially the same. They've got checksum blocks at the top, they've got floating records with IDs in them, there's a free space list, and so on. So when you actually look at these things just at disk pages, they don't look very different. So we're going to take advantage of that. And we see we have all these rings, the implementation, all these ring structures are actually pointers inside the database because that's how the navigation works. Now, obviously, we're going to relational databases, so those pointers have to go poof into something, and that's going to be a join table. So the essence of this approach is very simple. We're going to read physically all the pages in the legacy database. We're going to move those pages block by block, sort of block move them over and reshape them as relational database pages. Quite a straightforward operation. We're going to capture the mapping, what was the disk address in the old database, what's the disk address in the new database, and what were the types of the records. And I'm also going to capture the pointer mappings because I'll let the picture disappear, but there's lots of pointers in this network database. So we'll essentially keep track of where those pointers pointed to in the old database, and we'll keep the types. And we'll also keep the record that they're going to. Given these, we can just block by block move the entire legacy database to the new database. And the really exciting thing, because my machine's already saturated, I can actually do this from a dump tape or dump block or parallel access to the actual disk controllers. I can do it on the new hardware. So I'm not going to break production of the existing system because if I'm going to be moving terabytes and terabytes of data, I don't want to be interfering with the production system. That's one of the key tricks. So at the end, then we just do a sort merge, essentially like this ref-def match, except we're doing it over a huge amount of disk space. And we basically go and just patch, fix up all the physical records. Very simple algorithm. Still pretty scary, but simple. And I just move along. I think everybody knows that binary is better than batch. Binary is better. If you know nothing else, please do not use JSON unless you have a permit. You want to find out how to waste a lot of machine cycles, basically how to make your data so you can't figure out what it is. Make sure it's schemaless, by the way. That way, when you add some fields, you'll have to know what day you added them because you don't have a schema to see them. I can't believe how many people still do this. The other thing is batch is better. If you really want to go fast, if you really want a high throughput, you're not going to have a real-time system unless it's a batch system. So you'll process like 1,000 transactions at a time. And people in Chicago know this in the financial community already. There's a couple of error messaging things from Martin Thompson that very much explore this. So this really favors processing. The other thing is much simpler, so correctness is much easier to reason about. Now, one of the things that's very important here is that we serialize things quickly. And so the best serialization technique I'm aware of goes back before protocol buffers. And actually, it's much like something now called Captain Proto. But basically, you have a set of objects or records in memory or disk. And what you do is you grab memory, a chunk of memory, and you pack them into that memory, and you just change all the pointers to offset pointers. Once the things are converted to offset pointers, you can transmit the data in a block, and then you can just relocate those pointers. And then you can, to do this, you have to have access to the underlying sort of GC mechanisms, but basically you can lay it out in your Java space or your C# space, and you can say, okay, I've got this physical chunk, become objects, which is very straightforward to do with you have to know something about the JVM or the C#, but it's still pretty easy. So the big thing is that some people would think of this as a risky operation. So we want to give the customer some confidence. Not only want to give the customers confidence, we're actually terrified that this thing might not work. Right? We're going to be moving, hundreds of thousands of database pages at every customer site, unattended. So first thing is the algorithm is specified using a very old technique called decision tables. Table-driven programming is still one of the easiest ways to verify things, since basically you can have state tables, decision tables, and constraint tables, and much of life can be done with those. These are very straightforward to verify and implement. In fact, the implementation can be automated. The other thing is we wanted to prototype the algorithm to see whether it worked. So to prototype it, we basically wrote a prototype code in a functional array language. So if you see some J code up here in a second, you'll know what it was for. And we were very quickly able to prototype using a large in-memory implementation that the algorithms actually worked. So our confidence is getting up. We reviewed the decision tables, did an implementation. And the other thing is said, well, when we're moving all the code, because we're going to taking bit pack fields and various other things in the ugly old database and doing something else weird with them when we put them in the new database. That migration, that simple moving, could be bugs. So what we did is we generated, from the two schemas, we generated the source code. So we could actually see in the source code of the language, and we can generate the source code for, C on one side and, PLS on the other side. You won't know what PLS is, but there is a language called PLS, which is what you had to use to talk to this database. So, and having the source code means you can efficiently, You know it'll run as fast as you can run on the platform. It's straightforward to review because it's basically just move operations. And the other thing is you can actually now do database restructuring because this is the place where you can put in the code to split records, add fields, do all those things that you wish you could have done through a restructuring activity. So I think let me just go back. So that it turns out that this is one of the few times that you can actually refactor. Have you ever seen a database refactoring tool? Because there aren't any that I know of. But it turns out that using exactly the same techniques, you can basically transform that existing schema in a new schema, and all of the operations can be done by essentially just putting extensions here to move, remove, add records, whatever, because they're all just something that can be done on the physical store with the fix hubs. So you can do the refactoring as well. We didn't mention that at the first time because we didn't want to offer that feature, but it's really quite straightforward to provide it. So the question comes, how do we have confidence in this? Because these are not the sort of things that you get to, let's try it. Oh, it didn't work, we'll try it again, right? We sent it to 10 customers and, the first 10 customers didn't know what they were doing, so they just let it run until it finished. Nobody checked it. So first thing we need to do is look at the design. So the design, basically, we have these decision tables, that's what they look like. That's actually a fraction of the real code. The tables are quite small. And then we had a prototype, and for those who were a Venkat fan of functional programming, that's some J code. And then we did something. Remember, we generated all the source code to move the blocks from the legacy system to the new system. So then we reviewed that source code. And since this stuff is pretty scary, we actually reviewed it with 2 independent teams. All these things were done by having 2 teams looking at this. It's a very old technique, but it's, many old people have found that you can write the same program twice with 2 different people fairly quickly, especially if you modularize it in tables and so on like this. So that we're using a technique called IV&V, which basically is 2 different teams writing not all of the code, but some of the code, and I'll explain what I mean there in a second. So having done the review, now we have confidence. We can start looking at the implementation. So the implementation testing, first of all, before we do anything else, databases are out there spinning around for a long time. And believe it or not, not every page or relationship in the database is in great shape. There are just a lot of places where the elephant came in at night and stomped on a lot of your database pages. And that's why one of the reasons why you can't also write queries, because often there's pages in the database that you can't read because they've been stomped on for some reason. And if you try and migrate data that's been stomped on, you end up throwing exceptions all the time. Now, some people think that's fine, but when you're moving, hundreds of terabytes of data, you really don't want, the thing to stop and say, well, let's run it over or see what this problem is. So before you do anything, you write a health check. And the health check uses exactly the same algorithms because essentially all you really have to do is validate that those pointer rings are accurate and that the checksums and everything that are on the physical data pages are correct. And the other thing you can do is the health check routine can usually fix up the database in the sense that it can at least fix up the page so it's not going to cause the migration software to crash. Not going to throw an exception. So now you've got the health check in place. This is also handy because you can run the same implementation on the new database to make sure that it also, you didn't smash the database pages or put them in incorrectly. Because again, most people don't ever see physical database pages. So you want to be very careful about doing this. I'm not advocating this is something everybody should go back and say, I think we should do this. But it is the only way out of this hole that I know of, if you really want to deal with it. Then we do lots of tests. First we test that we produce the files correctly, which is easy to do, that we've got these sort merge files produced correctly. We look at the source code. We check that we can actually move, that we can actually take a physical page from one database, move it to the other one, and actually go and look and verify those bits. And then, once again, review the actual implementation. Now we get to the migration validation. And how do we test this? Michael had to run away. I could talk about, hey, let's write some unit tests for this. Come on, fill your boots. You will die trying to unit test something like this. You have to come up with a different idea. And the different idea, again, involves the same principles. One is we need a check to know things are there. That's an aggregate check. And the other is that we need to be able to inspect this and verify it ourselves. So we can do random inspection for that. So validation, I mentioned there were two teams. One of the teams they're only worried about doing the validation. So they're going to write a quick and dirty version of the migration thing because they're not going to actually move any of the records. They're just going to check some. So they're essentially going to construct a set of invariants over these databases which have to be true. They're going to implement those invariants, which means looking at the data and also looking at the relationships that are being there. They'll use the same file structure that I talked about. And they will run that completely independently. As soon as the database has been migrated, they'll run the validation algorithms on the new target database. This provides rock-solid assurance that the data has come across from the legacy system to the new system and being preserved. So this is really, it was a fun project. I mean, a little scary at times. I have to say that my grad students that worked on this, recent hires, didn't know how scary it was. I'm a big fan of Seymour Cray. Hire them young, they don't know it can't be done. They were terrified when they actually learned what the algorithms were going to be doing and the scale that they were running. But the assurance we had through validation was invaluable because it found all sorts of bugs during the implementation and the first few runs and so on. So we gained a very, very high confidence level through doing this. And I just mention it because I think it's interesting to think about, people have all these approaches. I mean, property-based testing is the best practice, which the Agile community may learn someday. But there are other ways to test systems besides writing classical test cases. And the validation is in fact an implementation of a kind of property-based testing where we're certifying these invariants. So this is a very powerful way to go. So, job done. Great. Ship it out to the customers, no problem. Oh, there is one other problem. These customers have legacy code that reads and writes this database. Oh, okay, Dave, what's your magic trick for doing this? Well, I'm going to disappoint you because not everything is a free lunch with magic tricks. Some things are just, we've got to rewrite some code. But we can try and apply a disciplined approach for doing this. First thing is that when we analyze the legacy code, we identify all the readers and writers. Customers can have that too, so they can verify their own code if they got. So again, we get essentially tables, large ones, databases of reader and writer identification. Now, of course, we wanted to write something that would automatically translate these DML queries in the network database and turn them into relational queries and so on. And that was a very interesting research problem, but there's a lot of risk that it would go wrong. And since most of the query code was already replaced by people going to SQL, so they didn't need most of the reader problems are just solved by people just migrating to SQL code and using reporting generators. So for this customer, this wasn't a big problem. But for the complicated queries, which had to do these recursive transitive joins over the transitive closure, which were done through pointer walking, there was no solution. We had no magic, had to rewrite those in modern SQL, for which there are things to do, operations over the transitive closure. And in a couple of cases, we had to go to essentially embedded SQL, where you've got C code, which is basically talking to moving cursors and things like that. Not something you want to do for many things, but again, we reduced the percentage of that to some small bit. And so what that allowed is basically to migrate a whole lot of customers with a complicated problem off of scary but risky technology to a modern world. Well, modern to them, a relational database world. Right? I think most things are going to end up looking like relational databases. So, I think no SQL will probably be dead within 2025. So the point of this talk is not that this was a brilliant decision. I had some brilliant students, graduates, recent grads who helped, but rather it was just looking at a very scary problem and trying to break it down with different techniques and using things from different generations in time. Decision tables come from the 1960s, 70s at best. Functional programming, J was a pretty advanced thing to do at the time, still is. But it allowed us to do this. Moving the physical pages and doing that, those are tricks. Basically, if you worked a lot on garbage collectors and systems for managing large modern object stores, these are techniques that come from that era. Generating the source code is basically a way to make things to be transparent so you can read it and also get portability. And sort merge is just a way to not be memory bound, for actually dealing with this, and the algorithms are established. So the innovation here is thinking, coming up with a way to take a very risky problem and break it down into small bits that you and a small team of people, or ideally just them, go off and do. And taking into account that you couldn't take these systems down, they're running live, and since they're running on legacy machines, those machines are maxed already. So finding a way to say, well, perhaps we can run the migration on the new hardware as opposed to keep trying to stress the old hardware. So the other thing about this is it was a really fun project. was very satisfying, wonderful engineering experience. And there's tons of these opportunities out there. So when someone says, oh, I got to put on a legacy team on this old system that really sucks. They don't even program in C, right? Don't think of it necessarily as a really bad job. I have to say I've learned a lot more working on some of these really complicated messes than I have working with some of the newer, sexiest technologies. And the customer satisfaction, if something turns you on, for me it's building an application that a customer uses. There were customers virtually in tears because they didn't believe the problem was solved. They saw somehow manually they were going to have to rewrite the whole system and do it. And the other sort of point is, please don't rewrite. And please stop lying when you say refactor, when you're rewriting. Technical debt and refactoring, you'll hear from Kent, I'm sure, have a meaning. And when Ward and Kent quote those terms, and Venkat mentioned, it's basically cleaning up the little bits over days. It's not fixing your mess that you've ignored for days because you're busy, doing agile stuff, and then you basically have a mess, so you have to beg for technical debt cards. Stop telling your executives, we're going to solve our business by refactoring the code. When you're lying, it's not equivalence preserving. There are no decent refactoring, there are no decent rewrite tools. And for large code bases, there are very few decent refactoring tools or practices. Most of these things end up in a mess. Most of them take 2 or 3 years. This was done in a period of months. Often you can make a difference by looking at that part of the legacy system which really has the value and which is the bottleneck, and inserting new technology, new algorithms at a few points rather than rewriting, replatforming anything. Anyway, thank you very much for your time.